Good morning, everyone. I am Alaric Montenon. I'm a researcher at the Cyprus Institute, and basically our field, as you saw from my colleague Kypros, that we're working on solar concentrated application, but we have some, let's say, domains of convergence with HVAC related fields, and you will see how. So I'm going to speak about the linear Fresnel collectors that you have seen. It's one of the 4 technologies which is a linear technology. So everything started from the fact that, as you know, that from a focal point to a lens, we can, if we're well located, we can see the beams going through at the infinite. Okay, this is something that we really know. And in the 18th century, there is a French physicist who decided that maybe we could try to grind the material so we would have something that is thinner. So in that respect, we will have less losses in terms of transmission. So less material, especially at that time where the materials were not as good as we have now. Afterwards, a bit later, another French physicist called Condorcet decided that maybe we can have a multifaceted approach, so even having even smaller pieces and different pieces. And afterwards, 1 century later, Augustin Fresnel, so the name we use for this kind of collector, was asked by the French crown to do something about the lighthouses. Because the lighthouses at that time, 200 years ago, they were made with these thick lenses, and actually there were many losses, optical losses, and this was not avoiding, let's say, the fact that people, the navigators, would end up in shipwrecks. So he has been asked to work on an optical system for this lighthouse in one of the estuaries there, the Gironde, and basically he applied all these optical aspects that you saw before from the 2 previous physicists, and the light could be seen up to 32 kilometers away. So that was really a breakthrough, and this technique has been applied afterwards to almost all the lighthouses in the world. So that was like 200 years ago. This technique is already used a bit everywhere in our application, and especially in the lights of the cars. So how did we end up from Augustin Fresnel, the French physicist, down to the collectors? It's just doing so. We rotate it, so from the sun we concentrate the light on one absorber. The work of solar concentration has started, let's say, in terms of application, although the principle is known from Archimedes when he was in his Greek colony in Sicily, in Syracuse, 150 years ago, around, more or less. Augustin Mouchot, for the Universal Exhibition in Paris, decided to design a steam engine that would work with a parabola, and he would print papers with that. A bit later, in Italy, now we move to Italy, Alessandro Battaglia said that maybe what we can do instead, and like what Mouchot is doing, where we have to track the sun, and at that, obviously at that time, in 1878, we couldn't track the sun in an automated way as we can do today. He decided that maybe what we can do is to have several so-called receivers, but they were not receivers, several mirrors, and just having them moving while the receiver itself there will be fixed. So that was the first approach of having linear Fresnel collectors. He developed a patent, as you can see, in 1886, but the application has been not accomplished. It's like around 80 years later that another Italian, Giovanni Francia, he developed an optical system that is, we can say, the first Fresnel collector. As you can see here, linear mirrors, as my colleague Kypros has showed you before, and one line receiver. That design was not really efficient, but it could still produce steam up to 450 with a peak optical efficiency of 60%. So it means that from the radiation, how much energy we can give to the steam. So 3 main components in the Fresnel collector. The first is what we call the primary reflector, because there are 2 stages of reflection. The first one, the linear mirrors here, are tracking the sun, and they reflect the light on what we call an absorber. This absorber will host the heat transfer fluid, and along the line will get heated up. There is a secondary optical reflector. This is a very important feature for this specific concentration technology, is that all the spillage here can be recovered and sometimes can be co-designed, so in a way we can harmonize the flux that is going around the pipe. This is the Fresnel collector, so the second solar facility that we have in terms of concentration at the Cyprus Institute. This is in Aglanja, so at the border of the Athalassa Park, on the northern part. So in 2016, we have commissioned this collector here, which is on top of a roof. It is made of 288 mirrors. The reflective area, so meaning all the sum of the areas of each of the mirrors, is 184 square meters, with a receiver which is 32 meters long. It has an average concentration of 26, so average concentration is basically each unit surface of the absorber tube there. If you look at it, how many suns this surface will be able to see, so 26. So it's like having 26 times the sun in front of us. So as you can imagine, this requires a lot of solar cream if you're just in front. So, but still, this ratio of 26 is low, and I mean, in terms of solar concentration. Technologies that are using central receiver, like in Proteas, they can go to thousands, several thousands. In the case of solar furnaces, you can go to up to 10,000. So this means that in front of you, if you're on the receiver, you have 10,000 times the sun. We have 72 motors, so it requires a lot of tracking devices, and we use a heat transfer fluid, which is oil, mineral oil, that is heated up to 180 degrees. This technology can go now to much higher temperature, but in the scope of the project, we wanted to stay at low temperature, because the higher the temperature, the higher the pressure mitigation. And we are in the built environment. The building you see under is almost 50 years old. We wanted to stay on the safe side. But we demonstrated that it was possible. As you see, the building itself, although it was old, we have used the structural beams under to put hosting beams where we could sit the Fresnel on it, the linear Fresnel collector on it. So it's more or less 30 kilograms per square meter. The advantage of such, especially here in Cyprus and also relevant for the Near East countries, is the fact that this kind of collector, by the fact of being on a roof by itself, just is a radiation shield. So over the summer, you avoid the radiation to heat up the building itself. So you avoid extra cooling. So the facility that you have seen, the linear Fresnel collector, is able to supply to the adjacent building more or less 1/3 of the heating and cooling needs of the building here. We could go to much higher in other conditions, but here we have a couple of laboratories in this building that are consuming a lot of cooling, so that's why. But if it was for office use, we would be around 2/3 of the needs of the building. So you see here the absorber. We use usually an ISO 9806 to define the operation mode, so I will not go into the details, but it's basically the energy we receive is just a matter of the optical efficiency minus the heat losses and the thermal inertia. The linear Fresnel collector has been built through the STS-MED project, so it was a European project including also countries from the Middle East and North Africa, and it was made of 6 countries with 14 partners, and the idea was is that all these countries here, they are in the sunny areas, and we wanted to comply directly to the needs of the very end user at its premises. So that was something that was really relevant for all of us. And 4 collectors have been built. So you can see the 4 collectors. So this is the one of the Cyprus Institute, and the building where it's supplying heating and cooling to. This is the one in Palermo. So 3 lines of linear Fresnel collectors. 1 twin collector, Fresnel collector also in Egypt, Sechem, which is supplying heating and cooling to a nearby hospital, but also desalinated water and electricity with an organic chlorine cycle. And this is the one in EinB in Jordan with the parabolic trough collector, so one of the 4 technologies that you have seen from my colleague. And it's also producing hot domestic water and steam for electricity and cooling via an absorption chiller. So one of the applications of the linear Fresnel collectors, as you see, and that's why I started with that, is that it can be linked to heating and cooling demand of the buildings, and also hot domestic water, and also supply of water. But one of the main use of these kind of collectors generally is more for heat processing. Why heat processing? Is because 75% of the demand of energy from the industries is heat. They don't need anything else, they need heat. And this heat that they need represent 25% of the emissions in the world. Why? Because they are mainly supplied by biomass, fossil fuels, and electricity, but this electricity can be itself produced, like in Cyprus, 90% from fossil fuels. So at the end, heat processing, and even before, the International Energy Agency was not taking into account these emissions, but they are very tremendous. I mean, they represent a lot of emissions. And 3/4 of the heat that is required by the heat industry is less than 400 degrees. So the linear Fresnel collectors, not only them, the parabolic for instance, they are able to respond to 1/5 of the heat demand in the world, which is very very important number. And it's not only that, is that these kind of collectors, they can be integrated directly on the facilities of the end user, as we have been doing with our Fresnel collector in the built environment in Aglanja. So one of the potential use is the use of linear Fresnel collector, as you see here, with a V shape from Rio Glass in Seville, Spain. So they're using this absorber here to treat the water, the sludge from the mines. As you know, usually the mine industry, they just use the wastewater and they put it in large ponds, and the water is green, blue, you know, but at least from the color you understand that it's highly contaminated, it's open air, and obviously it's a source of pollution. So Rio Glass, they have developed a solution where you just throw the sludge in, or you have you plug it to a zero liquid discharge system. So it means that you totally evaporate the water and you end up only with solid minerals. And obviously it's much better to have solid package of minerals that we can treat instead of having open air ponds. The advantage also of this kind of system is that they are modular. You can have them side by side. Another very important utilization of this kind of linear Fresnel collector from industrial solar here. They were pioneers in the world, let's say in the 2 previous decades, about deploying this kind of technologies, that you can produce also steam directly for the pharmacy industry on their roof. So here they produce steam up to 160 degrees, and this is in type in Jordan, and they save up to 30% of their fuel demand on the facility. Another use is also for the food industry. So this is an example that is made in France. So now we're using an open loop of air. Air is being pumped into the receiver directly, and the air is heated up to 250 degrees. So basically, the air is heated up and goes first to the process here, basically for the production of marmalade. So it's located as a solar roof for parking. The cars may park under, and we produce here the marmalade with the steam. And over the day, if there is overproduction, they send simply the heat into the rocks, like a sauna approach. So, and when, by night, when this is full, we can revert the process this way. So air is being blown from outside, heated up by the rocks, and supplying the process. So that's the main advantage of this technology, is that we can store the energy in friendly materials. unlike lithium, unlike cobalt, or any elements of the batteries that we import from abroad, they are also fossil fuels, these materials from the batteries. They need mining technologies and just to be extracted. In Europe, we receive them, they are well packed, they are nice, but we don't really care about the environmental impacts that they may have, for instance, in China, just to say it. And also, the batteries are made of rare earth. And I don't know if you heard about it, but the rare earth market is monopolized by China, a bit by Russia, and the context is not really good for us as Europeans, because we don't have access to these technologies, these minerals. Another use potentially is also for the food industries, is for the butchers. This is an example in Spain. So Solatom is developing small units of 15 kilowatt. You see they are very light also. They can be installed with a forklift in 1 hour on the roof of the facility. And this kind of technology used to be very expensive, but now, let's say, for small businesses in Spain, and especially in the context where, the mainland Europe, where the electricity cost is going very high, this starts to be competitive. So they can supply the heat needs of the meat industry directly on the premises, saving money for the supply of heat. In other cases, this has been used also, like you see here in Sardinia, in Italy, for dairy products. So they are producing local cheese, Sardinian traditional cheese, and the side effect, the beneficial side effect is that they can use these, so the sheep can breathe under. So it brings also shade for the animals, and obviously it helps let's say, at least to extend the life of the grass under. As you see, they can save more than 500,000 liters of oil, and it prevents a huge amount of emissions in the air as well. The main drawback of these technologies is that we're using mirrors. Photovoltaic panels, they can still produce even if they're a bit dusty. And they produce, let's say, quite well. In our case, we're really subjected to this surface, and we need really the mirrors to be clean, to be optimal, because we rely on direct normal irradiation. It means that we need to have clear sky. If there is a cloud in front of the sun, we don't produce anything. Unlike photovoltaics that can be produced even from diffuse radiation, any diffuse radiation. So the water is a clear issue for us. We need the cleaning to be done with a reduced amount of water, simply because where there is sun, a lot of sun, like in our region, there is water scarcity. So if we, at the end, we just transpose our issue of energy down to the water use, it's not good. So it's just transposition of one issue to another one. So there are some companies like the Fresnel with 2L, this company that develops solutions that is able to clean, as you see, with a very little amount of water, their field. So it's just like, some of them, they have shape of a spider or monkey, and you just put them on the mirrors and it will do its job on its own.
You have 1 minute, Alaric.
All right. There are some also homemade solutions that can be done, or Fresnel collectors for cooking. And just for you to know that in Cyprus, the amount of solar radiation that is received on top of the island is more than the whole energy required by Europe in a year. Imagine, the whole solar radiation that is received on top of the island is more than all what Europe requires in a year, and I'm including even UK. You have to know that. There was a world pioneer. I mean, he's still a world pioneer, Sotiris Kalogiru, from CUT in Limassol. He worked a lot on the application of these technologies, and you see all the sectors, like for dairy, for textile, paper, chemical industry, and bricks and rocks, plastics, this kind of technology can be used. And I will finish with this. My colleague has shown one photograph of it. While in Europe, we're wondering if this technology is not possible or not. It's very expensive, capital cost, and so on. The Chinese, they're making it. And see the size of the Fresnel collector. They heat up molten salts up to almost 600 degrees. They did it. We have been wondering in the Western countries if it's possible or not. They are just doing it. And they produce electricity. They can work 24 hours because they have 13 hours of storage. So this technology, the main advantage and the key point is the storage in friendly materials. Our challenges is that of this technology is that the more efficient we want to be, the more expensive it is, and it's not linear, it's exponential. The linear Fresnel collector is a good trade-off. Why? Because we can simply have a technology that is not as efficient as a central receiver like in Proteas. Maybe we lose 10% of efficiency, but it's much cheaper. It's virtuous because we can create local jobs for the maintenance and also for the production of the collector itself. And with that, I will thank you. You see my email. If you want to have more information, you can, in my phone, you can contact me. And there are also some material that is available on YouTube where you can see what we're doing in terms of solar concentration. There is also a virtual tour of this facility that is available online. So if you want to have access to it, just send me an email. Thank you.